I'm not really a master when it comes to either of those programs. But this will be my Calc 1 project.
No title?
Huh?
I like the title, Archimedes. Well, what's it? That's your title.
Well, that's not my title. That's just what I named it.
Okay.
This is about the brachistochrone curve. It was something that was already done by, it was discovered in ancient Rome. They were basically doing the exact same experiment as me, where the curve, it was asked whether a line, a parabola, a circle, cycloid, or a 6-degree polynomial, or even just a straight line going down and to the side, would, if something was moving along those lines and curves, which one would get to the bottom fastest, right? Basically the same exact experiment I was doing as a slide, where, you would start here and end here. A lot of times when you think about what's the fastest way from one point to another point from A to B is usually a straight line. But when taking into account upwards and downwards motion, that's not necessarily the case most times. It usually isn't. So they tried to figure out if it was the line, the parabola, or which one of these it was, and they did multiple experiments with such things over the years.
Romans, do you say?
Yes. The Brachistone curve, it was first discovered in ancient Greece and experimented by the Romans. The word brachistochrone is described from brachistos chronos, meaning shortest time in Greek. Chronos was the Greek and Roman god for time and time travel and things like that, and brachistos is their word for shortest. The curve itself is a cycloid, which is essentially half of a circle. This one right here. It they did the experiment. I had this one right here. I liked it because it was a GIF, actually, that these little points were being shown moving, but I couldn't get it to work on here. They showed it go from here to here, from here to here, and actually taking the curve. And I decided to put that slide in because of where I wrote on the board last time and was wondering which one would actually work. It proves that the curve works. And 5 mathematicians responded with solutions. They thought of the problem in the similar nature, the fastest way down. They all came to the same solution, or at least it was similar to where the cycloid was, was the answer to their problem. They all, instead of a straight line, they decided the curve was the best way to go. And I accidentally thought it was called cycloids instead of cycloids. So you'll see that a few times. A cycloid is half of a circle, which was which we discussed in class when trying to find the answer to the area of a circle. Remember the presentation that we did, where it was half of a circle. I remember we did a presentation like that when you discussed the area of a circle.
Yeah.
The equations for the cycloid are xt equals rt minus sine t plus xo, which is, this is the radius, this is, t is a constant multiplied by your pi, whichever pi you're needing, because it's an equation that goes back and forth, like the sine or cosine equation. You're multiplying it by that to find it, and then you add your x or y initial, whichever one. The y equation is r times -1 plus cosine t plus y initial. They're both two separate equations that have nothing to do with each other. They are just combined together to make this specific equation necessary. I have it in Excel. I've made a graph of it, and I have one of the revolutions is a perfect example. R is the radius of the half circle. T is the theta, the tangent line of the points from 0 to 2 pi. And in this example, only 0 to pi is used because of it being a half circle. The curve is a cycloid that is rotated on an axis where the first tangent line is a 90-degree angle pointing downwards. It's this exact curve where, it's like this, is the original curve where it was rotated along this line. And that's the end of this actual slideshow. In Excel, I have the curve itself. This is all the math for it. Here's the equations. xt equals rt sine t. The r, I just used the flat line radius. I used it by the distance formula, just finding the distance from here to there. This right here actually is the shape of the slide that would be needed, or like a water slide, where it would actually have to go slightly underground for it to make it the fastest way down, and then it'd have to come back up slightly, 100.
No, I don't think this is right. No, the previous picture was the right one.
The previous picture? This one?
This one, yeah. So this is, the cycloid is the curve traced by a point on the rolling wheel. So if you attach like a reflector to a rolling wheel, you will see a cycloid in the dark doing this. So that's roughly what this is, except it's upside down. That circle over there on the right is that circle, is that wheel rolling, and that point will be tracing out the curve that is the red one, or the blue one. Probably it's the same thing. But the problem, the problem is that it is not. So it's not a circle for one. The equation that you have represents the x-y coordinates separately. So these are x and y, and there is no t or whatever, or the theta you use. So that's how we form curves as they move through space, because t is time. Okay, but that's not the same time as in the problem of Barkhister-Krohn. Because that's just the way. If you represent the cycloid in the way of rolling wheel, then that formulas that you have give you the time where that point is located, and it traces out the cycloid. But your object sliding down cycloid will not be moving along those equations, along the same curve, but with different equations, because it will be spinning up. Okay, so in a way it's the exact opposite, I suppose. Well, it actually goes faster at the top, and that's what I was wondering about, if there is any way to actually connect the two, so we know where the cycloid comes from. It comes from the rolling wheel, okay, but which seems to be probably very straightforward. What does it have to do with the sliding object on it? And there might be some connection there, but just I'm not aware of what that is.
The Brachistochrome curve itself is a cycloid. It's just a slightly altered cycloid.
Why is it so altered? I think it's just the straight. That's the.
This is the actual curve itself. You see, it's not a perfect cycloid. It's altered slightly.
Are you sure?
Yes, I am. Well, at least the sources that I had said so.
Well, the previous picture, which indicates the this is the cycloid. This is the cycloid. It does not dip, the black one. It does not dip below the surface, which is what the problem I have with the next picture. That is my understanding, is that it does not dip. If you dip below the surface, you are sort of losing time. That has been my understanding of the problem. And that picture reflects it. So straight line, the polynomial, circle, the parabola, they're all no good in comparison to the cycloid. And the cycloid, it goes, as you can see, it dips below the circle, but does not dip below the end point of your trip. I don't know. You probably can make some kind of physics case that why the losing energy, you're going down. Maybe I can't really do that, but there must be a way to actually demonstrate that. It probably doesn't make sense to go below the level and then climb back. But your picture says that this is has been my understanding of the answer is this the cycloid looks like this, made of the curve itself comes from a rolling wheel. So I don't know where the next picture, the previous one, where it came from.
I might have done my math wrong, and maybe the source that I found it from also did their math wrong as well, and found this curve. That could have been the error.
Okay, well, yeah. So you do try to sort it out, but I'm afraid we're out of time now.
Mm-hmm.
Okay, so thanks. We'll continue next time with